Hey guys, this is group 6. So today we'll present paper named Teacher-Student Curriculum Learning.
In this presentation, our team will walk you through the background and motivation behind this framework of curriculum learning. We will also explain the framework and the approach in detail. We'll discuss the experiments conducted in the paper and then we'll briefly talk about the suggestions or further improvements that we propose for this model. As the paper talks about a framework in curriculum learning, I would first like to talk briefly about what reinforcement learning is. So, RL is basically a machine learning algorithm in which an agent learns a strategy through interactions with the environment. Let us try to understand this by using an example of a cat. In this scenario, consider your cat is the agent, your house is the environment, and state could be anything like your cat is sitting or it's walking. Now, cat can react to any situation by taking actions, which is nothing but transition from one state to the other. We know that we cannot tell a cat what to do and what not to do. Instead, what we can do is we can create a situation for the cat and it will react to the situation in many ways. If the cat responds to a situation in the desired way, we give it a reward, like it could be a fish. When the cat sees the similar situation again, it will execute the same action. This is the whole idea of reinforcement learning. Any agent, it could be anything, it could be a robotic arm, it could be an agent which tries to solve a game. So your agent is exposed to an environment, it takes some action, records the reward, and learns from it, and it tries to maximize the reward. Now, deep RL is something which uses deep learning and RL principles to solve a wide range of complex decision-making tasks. Say, for example, you have a robot which wants to pick and place some objects from a table. So that's something which is solved using RL. Or you can have another scenario where you just want to play a video game using an RL agent. But in a number of real world scenarios, the agent faces a challenge of sparse rewards, which is when the states that returns a positive reward are very very less in the entire state space. An example would be when an agent has to reach a goal and it only receives a positive reward signal when the agent is very very close to the target. There are a lot of methods that have been proposed to deal with sparse reward environments. One such approach is to use curriculum learning. Curriculum learning tackles such problems by arranging tasks based on increasing difficulty. It is very similar to how we humans learn things. We first learn alphabets, we learn words, and then we learn how to form sentences out of these words. Similarly, as you can see in the picture, there is an example of an agent which is trying to learn how to play Pac-Man game. In the first task, it is given a very basic task. Is it just has one target and it has to reach that target. In the second case, you can see there are two orange lines which are nothing but lava, which is an added complexity to the environment. You can either introduce lava or balls. In the fourth example, you can see both lava and balls are introduced, making the environment or task difficult for the agent. So this is the idea of curriculum learning. You start by very easy task, and then you increase the difficulty only when the easier tasks are mastered. Further explanation about the process, about the approach will be explained in the coming slides.
Since the curriculum learning is to start with only easy examples of a task, then gradually increase task difficulties. However, define the difficulty of each task is not trivial, and human prior knowledge may not work at this area. Another challenge is to decide when to switch the task. Run static epochs for each task is not an optimal solution. May cause a time waste and overfitting problem for easy tasks. In the meantime, for difficult tasks, this will cause an underfit problem with deficient training time. The third challenge is exploration and the exploration selections. Should the algorithm choose explore new tasks or review previous tasks? And in the meantime, when the agent is exploring the new task, it may forget the knowledge he learned from the easy tasks. To solve these challenges, this paper proposed a teacher-student framework. So the teacher is to monitor the student's training process and select the subtasks for the students. And the student is trained specifically for each subtask. So between the teacher and the student, there's two bridges. The first one is a task. The teacher choose what kind of task for student to finish. So task can be a discrete subtask, or it can be the continuous task without clearly boundaries. And another thing is the scores to evaluate the difficulty of the task. So it can be the absolute total reward in reinforcement learning, or it can also be the validation accuracy for the supervised learning. So let's formulate these problems. There are two elements in the reinforcement learning. The first one is the agent, and the second thing is the environment. So for here, the teacher is the agent which choose the actions, and the student is a part of the environment which take the action and return the reward to the agent. So here the state ST is to represent the entire state of the student, like the neural network parameters. The action AT corresponds to the task chosen by the teacher, and the observation is score for the task the student achieved at time t. So for here, the reward is a change of the score for the task the student trained on. And there are two very important principles for the teacher to assign a task. The first one is that students should practice the task in making the most progress. And second thing that a student should practice on the tasks that are easy to forget. So let's look at the figure below. The left-hand side is a learning curve for students, and the right-hand side is a probability for each task. So in the beginning, the teacher tried to choose the action with the task that can maximize the slope. And when the students start making progress on task one, the teacher will allocate more probability mass to the task. So we can find out that the probability got increased. And when the student masters task one, the learning curve flattens and the teacher samples task one less often. At this point, student starts making progress on task two, and the teacher should sample more from task two. And this process continues until students master all tasks. And as all task learning curve flatten in the end, the teacher returns to a uniform sampling of tasks. Here we present a detailed algorithm for the teacher to do the task selections. So there are two main different approaches. The first one is the online algorithm, which is to select the task on air. And the second thing is offline, is to estimate the learning process by practice offline task several times, and the teacher choose a task based on the offline performance. The rest of the three algorithms are the offline algorithms.
After looking at the curriculum approach proposed by the authors, now we'll move on to experiments. In their first experiment, they took a very simple Minecraft game uh, to, to show the effectiveness of this curriculum learning strategy. So as you can see, they hand designed this Minecraft uh, map. So in the first, they only have the Pac-Man and the cheese. In the second stage, they have lava in between, and they slowly increase the complexity of the map. So this can be thought of as a five-step curriculum where you have five stages with increasing complexity. And now they use the approaches that we explained above on this map. and here are the results. So as you can see here, authors compare four different approaches. The blue line at the bottom is the baseline, which is the usual reinforcement learning we are used to, where authors directly train the agent on the most hard task, where Pac-Man is separated by a lava wall. And they also compare the results of their wind epsilon greedy approach, which is the best one, with the manual curriculum approach. So in the manual curriculum approach, they start, which is shown in red. Here they start with task 1 and then they switch the task 1 to task 2. So they see a drop in performance. And then the agent starts learning for task 2, and as soon as it has learned enough, again their proposed approach switch the tasks to task 3 and so on. And as per this result, both from training and evaluation perspective, window epsilon greedy performs the best. For their second experiment, authors took an example of one-dimensional digit addition. Although this sounds very simple, but for neural networks, this has been challenging from a very long time. And there have been many papers around this. So in this also, they find that online epsilon greedy algorithm performs the best uh, uh, with regard to any other reinforcement learning techniques. And on the right, it is shown that which task is sampled throughout the training process. So x-axis is number of epochs and on y-axis is the probability. So with this area, you can see that even though one digit addition was usually sampled a lot during the earlier phase of the training, similarly 2 and 3 digits, but because their approach also addresses catastrophic forgetting, they are sampling even the 2-digit or 3-digit tasks till the very end of the training so that they don't forget the addition of those.
We consider two further improvements. The first one is to increase the difficulty for the games. We can add more subtasks. So in the Minecraft experiment, the researcher only utilized 5 different subtasks. So the action space for the proposed method is limited. And this limited subtasks were also called the overfitting problems. So we want to increase the number of subtasks. The second improvement is to dynamic update the model structure of the student model. So for difficult tasks, student model can change the structure of the method by increasing the number of parameters, adding new layers, or change the active functions.